students, welcome to Shruti Academy. So let us start with the working of the linear induction motor. We have already seen the constructional features of the linear induction motor. Now let us move ahead towards the working of the linear induction motor. Okay, so here I have shown the three-phase induction motor, rotatory induction motor as well as the linear induction motor. Here I have been taking the single-sided linear induction motor. Okay. So as we were giving the supply to the stator of the rotatory induction motor, and a rotatory flux was being set up which used to travel along the whole of the stator. So in the similar way, as soon as we will be giving the supply to the primary of the linear induction motor, a flux will be set up. Now here the primary as well as the secondary all are flattened. Okay, so when they are flattened, a traveling wave flux will be generated, a traveling wave flux will be set up. Okay, and that flux wave will be traveling with a velocity Vs. We will be traveling with a velocity Vs. Okay, so let us say this is the traveling wave flux and this is traveling in a direction like this. Okay, so this is traveling wave flux phi. Okay, so this traveling wave flux is being set up now. Now what will happen? This traveling wave flux will be interlinked with the aluminium conductors, because here in the secondary the aluminium conductors are placed with a ferromagnetic core. Okay, so these will be getting interacted with this aluminium conductors, and in these aluminium conductors the induced currents will be set up. Now the induced currents, why they are set up? They are set up with two reasons. The first reason is there should be a relative motion, so they are being set up. The second reason is that there should be change in the magnetic field. So here there is no change in the magnetic field because the frequency is being fixed over here. Everywhere in India it is fixed. In India it is fixed at 50 Hertz, and everywhere in the world the frequency is being fixed. So there is no change in the frequency over here. So no change in the magnetic field, but there is surely the change in the relative motion. There is surely a relative motion between this traveling wave flux and aluminium conductors. So because of these this relative motion, the relative change over here, relative motion over here, induced currents will be set up in the secondary of the linear induction motor. Okay, so let us write down some points over here. So here the induced currents set up because of relative motion between traveling wave flux and aluminium conductors. Okay, so they are set up because of the relative motion between them, and so the induced currents are being set up in the secondary of the linear induction motor. Now what will happen? The secondary of the linear induction motor will generate its own magnetic field. It will be generating its own magnetic field. That magnetic field will be opposite of the magnetic field generated by this wave flux. It will be opposite and it will be repelling that magnetic field. Okay, so when that will be repelling, there would be interaction between both of them, and that would be repelling. The magnetic field would be repelling, and that will be generating a force. Rather over here we will be calling that force as upthrust over here. Okay, so that would be upthrust, and because we are keeping over here the secondary to be fixed, so our primary is free to move. So with that thrust, not upthrust, it is just the thrust. With that thrust, the primary will be start moving. Now here it is a translational motion machine or the device, so the motion will be translatory only, and so the primary will move ahead over here. Okay, because we have kept the secondary to be fixed, the primary will be moving in that direction. Okay, so this was all about how the motion is being taking place of the primary. We can also keep the primary fixed, and we can also allow the secondary to be moving. Okay, so now let us take some formulas, note down some formulas for the numericals. Okay, so we have already known that what is traveling wave flux. So let us assume Vs to be velocity of traveling wave flux. Okay, then Vr, velocity of secondary, okay. Then we will be having the power Pg, which is the air gap power, and we will be having the force, which is also known as the thrust over here. Okay, so the power, so what will be the force, the thrust formula given by thrust is equal to power upon velocity. Okay, actually the force on a conductor whenever it is related to the magnetic field depends upon three things: BIL, the product of BIL. B is the field intensity, strength, field strength. Then I is the current, and the L is the length of the conductor. Okay, so force is actually depending upon BIL, and with that force the thrust is being developed to the primary. So the thrust is given by power upon velocity. Now which power? This power is the Pg. It is the air gap power. It is the air gap power, or the power which is being transferred to the secondary of the linear induction motor. Okay, which velocity? It is Vs, the linear synchronous velocity. Vs is the velocity of the traveling wave flux, and it is also known as the linear synchronous velocity. Synchronous. It is also known as the linear synchronous velocity. Okay, so my thrust formula is Pg upon Vs. This is important from the numericals point of view. Now Vs is the linear synchronous velocity. So Vs is equal to 2ft. The Vs, linear synchronous velocity, is not depending upon the number of poles, but it is depending upon the pole width. It is depending upon the pole width. Okay, so T is the pole width over here. It is depending upon the pole width, or you can say pole pitch, pole width or pole pitch, and it is depending upon the frequency. F, everybody knows, it is the frequency. Okay, so my formula for Vs is 2ft. It is also important from the numericals point of view. Now over here also there is a slip, because Vr is the velocity of the secondary. Vr will be never equal to Vs, similar as it was in the three-phase induction motor. If it would be equal, then there would be no force or no induced currents. Okay, so it will be never equal. It will, in the three-phase induction motor, rotatory induction motor also, it was always trying to catch the synchronous speed, but it was never equal. Okay, so similarly over here the velocity of the secondary is given by Vr, and velocity of the traveling wave flux is given by Vs. So Vr will be never equal to Vs. So Vr will be never equal to Vs. Okay, so there will be a slip over here. The slip, the same concepts as the three-phase induction motor. The slip is also given by the same formula, Vs minus Vr upon Vs. Only thing is here everything is linear. Okay, so slip is given by Vs minus Vr upon Vs. If you are taking 1 and 2, you can write it down accordingly. Denominations. Okay, so the slip formula is here, and so Vr, the frequency, the speed of the secondary is given by 1 minus S into Vs. So this is yet another formula for the numericals point of view. So we have got 4 formulas over here. With these 4 formulas, we can easily calculate the numericals whichever being asked in the examinations. Okay, so this was all about the working of the linear induction motor. In this, the main concept is here only that as soon as the supply is given, the 3-phase supply is given, the traveling wave flux is being set up. Then with that traveling wave flux, that gets interacted with the aluminum conductors. Okay, so the induced currents are being set up. As soon as the induced currents are being set up, because of the relative motion between the traveling wave flux and the aluminum conductors, what will happen? They will generate their own magnetic field. As the magnetic field is being generated, that magnetic field will be repelling the magnetic field which was being set up by the traveling wave flux. Okay, and because of that, force is being set up. Now here the secondary is being fixed, so the force is being set up, and that with that force the primary tends to move ahead. And if it can be done otherwise also, the primary can be made fixed and the secondary can be moved. Okay, so the same concept is used in the trains, in the magnetic levitation. That all are the applications of the linear induction motor. So stay tuned. In the next video we will be learning about the advantages and disadvantages. Also we will be viewing some of the applications of the linear induction motor. So thank you. So please subscribe my channel, please share my videos, and if you have any doubt you can ask me in the comment section. Thank you.